Hello, everybody. So this is room 3 of the virtual ICM. And our second speaker today is Mark Mclean from the University of New York at Stony Brook. And the title of his talk is Floer Cohomology and Birational Geometry. Mark, I give you the floor.
Okay, so today I will be talking about Floer Cohomology and birational geometry. So Floer Cohomology groups have already been mentioned a few times earlier, but I thought I would explain a little bit here first. So Floer Cohomology or Floer homology is an infinite dimensional version of Morse homology. And so I should explain what Morse homology is. What is Morse homology? So with Morse homology, you start with a Morse function. So one way of describing a Morse function is as a smooth function, which locally looks like either a linear function plus a constant or a quadratic function plus a constant instead of a charts, local charts. Or equivalently, it's a smooth function where the critical points have non-degenerate Hessian, which is maybe the more standard way of describing it. So that's a Morse function, and we want to use that Morse function to study the manifold M, the topology of the manifold M. So a Morse function gives a cellular decomposition of the manifold M. How does it do that? Well, let's look at an example. So I have a manifold, it's a sphere embedded in R3, and my Morse function is the height. And it's sort of the sphere is bent into a U shape. And there are 4 critical points where the tangent space is horizontal. And for each critical point, I have a number, and that's the index of the critical point. And the index of the critical point is the dimension of the sum of the negative eigenspaces of the Hessian at that point, or of the associated quadratic function in that local chart. So how do we use this to study the topology of the sphere? Well, we look at the sub-level sets of the function f, so the set of points below a certain level. So let's look at the lowest sub-level set just above the minimum. Okay, and that's homotopic to a 0 cell. And then I raise my sub-level set a bit higher, so it's just above the index 1 critical point. And I get a 0 cell union a 1 cell up to homotopy. And then I raise it above the top of the manifold, and I get the whole sphere. I add 2 more 2 cells. You know, if a circle, you glue 2 cells, you get the 2 sphere. So with a Morse function, you get a cellular decomposition. The cells, the dimension of each set, there's a cell for each critical point. The dimension is the index of that critical point, and they're sort of glued together. And actually, the way you one way of gluing these cells is by you choose a metric on the manifold, and you look at the sort of gradient flow lines of the function sort of going down, and you use those gradient sort of flows to sort of glue the various cells together. Okay, and well, I want to compute, say, the homology of M. So well, if I have a Morse function and it describes a cellular decomposition, then I can compute cellular homology. And I want to translate the sort of usual definition of cellular homology into this sort of setup of Morse functions and gradient flow lines. Okay, so let's compute the homology of our manifold M. So the chain complex for Morse homology is the free Z module generated by the critical points, and it's graded by the index of those critical points. And then we need to compute the differential. So we choose some sort of generic Riemannian metric on the manifold M. And we look at the gradient flow lines that of the Morse function connecting critical points. So, well, you can describe the differential as a matrix because we have a Z module with a basis corresponding to the critical points. You just need to know what the entry corresponding to ij is, pi, pj. And that's just the sort of number of gradient flow lines connecting pi and pj, these critical points. But it's counted with sign. So they might have opposite signs and cancel. So let's do the example of the two-sphere that I had earlier. So again, I have 4 critical points. So this is my chain complex. It's z in degree 0 and 2, and z squared in it's free of rank 1 in degree 0 and 1, and free of rank 2 in degree 2. And then we need to compute the differential, and the red lines in the picture, those are the gradient flow lines connecting the critical points. And well, d of A is 0 because there's no flow lines going down from A. But d of B, well, it could be 2A or A minus A, and it turns out it's A minus A when you compute signs. And then there's one flow line from C to B and one flow line from D to B. So D of C is B and D of D is B. And so when you compute the homology, you get the homology of the two-sphere. Great. So that's Morse homology. And now we need to go to Floer homology. So what's Floer homology? Well, it's an infinite dimensional version of Morse homology. So there are many Floer groups sort of built in different ways. And I'm just going to look at a particular one. I'm going to look at something called Hamiltonian Floer cohomology. But there are all kinds of other Floer groups out there. So Hamiltonian Floer cohomology, I start with some data. I start with a symplectic manifold M. So this is some manifold with additional structure, which allows me to sort of write down Hamilton's equations for classical mechanics. And then I have a Hamiltonian, which sort of I use to describe the motion of my classical mechanical system, which is expressed as a flow of a vector field on the manifold M. And I want to know what my infinite dimensional manifold is, and it's going to be the free loop space of the symplectic manifold M. Okay, so the space of maps from the circle to M. And then I want my analog of the Morse function. Well, this is the action functional. So you know, the same sort of action functional you have in classical mechanics. The critical points will describe circles mapping to M, which are periodic orbits of motion of my Hamiltonian system. Well, another condition is that I need to choose H in such a way that it's actually formally Morse. So, you know, not every smooth function is Morse. You've got to perturb it generically, and the same here. I have to sort of perturb H generically so that this action functional is sort of Morse in some sense. And then I need to describe what the differential is. Well, oh no, what the critical, oh no, what is the differential? So, well, the critical points are one periodic orbits, one periodic solutions of Hamilton's equations with the Hamiltonian H. And well, what's a flow line? What's a gradient flow line? It's a path of loops, which is a cylinder. So it's going to be, it's going to be some map from the cylinder to M satisfying some PDE. And it turns out this PDE, if you sort of choose an appropriate sort of metric in this infinite dimensional manifold, this sort of PDE is some Cauchy-Riemann-like PDE, but possibly with a lower order term. Okay, so that's sort of very roughly what Floer cohomology is. I decided not to write the equations for the gradient flow line because they're impossible to solve anyway directly, and there's no point in sort of seeing them here. So here's a sort of schematic picture. Gamma minus and gamma plus are one periodic orbits of my Hamiltonian system, and I have some cylinder connecting them, solving my PDE. Okay, so what I want to do is I want to use Floer theory to understand some topics in birational geometry. And in particular, and the first thing I want to explain is the cohomological McKay correspondence. So let me explain what that is. So I have a finite subgroup of the special unitary group, and I look at the quotient Cn mod G, and I think of that as a variety. So the sort of, with a variety, you have a like ring of functions associated to it, which are, in this case, are the G invariant polynomials. And you describe it as a variety by looking at the relationships between those polynomials, and those sort of give you equations that cut out this variety as a sort of subset of Cn, or C complex affine space in some dimension. Okay. Now I'm going to resolve. So this is a singular variety, and so I resolve the singularities. So I have a resolution. So this is some proper birational morphism from a smooth variety Y to my singular space Cn mod G. I could think of this as like, you could think of this like a proper continuous map from a complex manifold, which is sort of holomorphic, where it's smooth and isomorphic onto its image away from the singularities. So that's a resolution. I want to sort of study what these resolutions are. I'm going to look at a special kind of resolution called Crepant resolution, and that's where the first Chern class of Y is 0. So another way of saying this is it's a smooth variety. So you take the highest wedge power of its tangent space and require that line bundle to be trivial as equivalent. Okay, so that's the sort of initial data. And now I want to state what the cohomological McKay correspondence is. So I'll state it as a conjecture. So for any Crepant resolution as above, there is a basis of the cohomology of Y consisting of conjugacy classes of G. Okay. Now, the Crepant condition is essential, because if I have some resolution, I can choose a point on it and blow up, and it completely changes the cohomology, increases the rank of cohomology. So I need this C1 equals 0 condition. Also, I should say Crepant resolutions don't necessarily exist, and they may not be unique in general. But this conjecture says that they all have the same cohomology. Well, actually, it's proven that they have the same cohomology. So yeah, Batirev showed that this conjecture is true when K is Q. And there's a proof of this theorem by Batirev using something called motivic integration, which is a kind of very sort of fancy Euler characteristic style argument. The reason why I'm mentioning this as well is because I think there's some sort of connection between, sort of loose connection between Floer theory and sort of this motivic integration. And so this is why I want to mention it here. Okay, so what I want to do is understand this Floer theoretically. So now I'm going to assume my resolution Y is scalar. I'm a symplectic geometer. I want a symplectic form on my resolution. And now I'm going to put a Hamiltonian on this symplectic manifold, and it's going to be some sort of rapidly enough increasing function of the radial coordinate. R to the 4 will do, but you could also choose like e to the r or some other very rapidly increasing function. So I have some function on y, that's my Hamiltonian. And then, well, I want to look at the Floer cohomology of this Hamiltonian, the Hamiltonian Floer cohomology, but it's not quite what I want, so I just need to change it very slightly. So it turns out there's a natural map from at the chain level from cochains on Y to the chain complex for Floer cohomology CF star H, and I take the cone of that map. So I do and I call this positive Floer cohomology HF star plus. And the way it's set up is I have a long exact sequence between singular cohomology of Y, Floer cohomology of H, and positive Floer cohomology of H. And so this is really the Floer group I want to look at. Okay, so here is the main theorem together with Alex Ritter. So suppose my field K has large enough characteristic, and then I put this additional very restrictive condition on that G acts freely away from 0, which I hope to get rid of in the future at some point. But for the moment, we have this very restrictive condition. And then what we do is we compute the Floer cohomology of this HF, this positive Floer cohomology of H in 2 different ways. And the first way is we show that it's isomorphic to the cohomology of our Crepin resolution. And then we show it is generated by conjugacy classes of G. And then as a direct corollary, we get the cohomological McKay correspondence. So this is a sort of Floer theoretic alternative proof of this McKay correspondence. So let me just give you a sort of idea of the proof of this theorem, a sort of very rough idea, so you can sort of at least see, maybe how one might approach, sort of compute these positive Floer cohomology groups. Okay, so recall I said there's a long exact sequence between HF star plus, HF star, and the cohomology. So to show that it's isomorphic to cohomology, you just have to show that the original Floer cohomology group is 0. It vanishes. And then we use a property of Floer cohomology, which is a nice property, which is if I deform my Hamiltonian in a compact set, it doesn't change the Floer group. And so what I can do is deform it in such a way that it vanishes in any given degree. So I fix a degree, and then I deform my Hamiltonian so I don't see any one periodic orbits of index, that given index. So I just deform it so that all the orbits have some large index way above the index that I'm interested in. And then that shows that it's 0 in each degree. So I've used this sort of deformation invariance property of Hamiltonian Floer cohomology. Okay, and then there's a different computational technique for for the second part of the proof, where I show that it's generated by conjugacy classes. And let's just go back to the Morse picture for a second. So I said in the original, like for instance, for the two-sphere, if I have just the two-sphere and my Morse function is the height function, I looked at the sub-level sets of my Morse function. And well, that gives you a filtration of that space. You know, it's a union of lower dimensional spaces, and it gives you a filtration of the corresponding chain complex. And so you get a spectral sequence computing that Morse homology. And similarly, you can filter by action. And if you filter by action appropriately, you get a spectral sequence, and then you compute the E1 page, and you hope that maybe it degenerates, right? Another observation is the orbits sort of go, if you remove this sort of origin where the singularity is, and G acts freely away from zero, so there's only a singularity at zero, well, that space is, you know, it's homotopic to a sphere modulo the action of G, which is free. And the orbits are, you know, up to homotopy correspond to sort of loops in this sphere mod G. And so they represent elements of pi zero of the free loop space of this sphere mod G, which is conjugacy classes of G. So there's a sort of explicit connection between these sort of loops, these solutions of Hamilton's equations, and conjugacy classes of G. Okay. Oh yeah, that's what I said. Okay, so now I want to give you another application of Floer cohomology to birational geometry. So I'm gonna, when I say Calabi-Yau manifold, I will just mean a smooth projective variety with trivial first-Chern classes, sort of maybe weaker than what some people are used to. And well, I say they're birational to each other if they're isomorphic outside the codimension one subset of each. And then there's a natural question, which is what properties do these have in common? Okay, so here is a lemma where I really use so Calabi-Yau as the condition C1 is 0. And if I have two birational Calabi-Yau manifolds, then it turns out they're actually isomorphic outside codimension 2 subsets. So complex codimension 2 or real codimension 4. You know, this is where you really need a Calabi-Yau condition because, you know, in general, a birational morphism could be a blow up and H2 changes. But I mean, yeah, so there could be a blow up and you know, it's not an isomorphism in that blow up locus. So why is this lemma true? Well, morally, it's true because if it wasn't true, there'd be some sort of codimension 1 subvariety, which would be sort of squashed to a lower dimensional variety in X hat, let's say. And that would create some Chern class, and then you'd have a contradiction. That's sort of morally why this is true. And as a corollary of this lemma, we have that H2 is the same. H1 is the same as well, and H0, and pi 1 and stuff. But I'm just, for me, I want to just mention that H2 is the same. Okay, so what about other homology or cohomology groups? So here's a theorem by Batirov again. Birational Calabi-Yau manifolds have the same Betti numbers. Okay. Again, the proof uses motivic integration. So that's maybe a hint that you should use Floer cohomology. Okay. However, if you look at the cohomology rings, they're different. pretty much in all examples, I think, that is sort of non-trivial. You can find nice examples of birational Calabi-Yau threefolds with different cohomology rings. So, well, what do you need to do? Well, you need to change what the cup product is. You have to add quantum corrections to the cup product. So I want to explain what the quantum cup product is. So first of all, I define a ring, the Novikov ring. And what is it? Well, it's formal power series. The coefficients of the power series are elements of my field K that I've just fixed. And the powers are elements of H2. So well, sort of maybe more precisely, you take the group ring of H2 and complete it using the symplectic form. So you have some ring, looks like some sort of power series. And then to define my quantum cup product, I need to choose a basis of cohomology. So I choose a homogeneous basis of cohomology, and then I have the associated dual basis, which I put hats on the A's. And it's dual with respect to the usual cup product pairing. And I use the definition won't depend on the choice of basis, but to sort of express it, it's easier to choose a basis. Okay. So to define small quantum cohomology, as a module, it's just cohomology over this power series ring, the Novikov ring. And then to specify the product, we just need to specify what AI times AJ is, and then sort of extend linearly over this ring. And this is the formula, okay? So AI times AJ is a sum of, you sum over all beta, and you sum over all M, and it's some coefficient, GW, standing for Gromov-Witten, which I'll explain in a second. And then you have the dual basis AM hat, element AM hat times T to the beta, okay? So this coefficient, GW, this is the number of holomorphic maps from P1 to X, representing the class beta and passing through cycles that are Poincare dual to these cohomology classes AI, AJ, and AK. A good thing to think about is what happens if there are no non-trivial holomorphic maps. If there are no non-trivial holomorphic maps, then you should get the usual cup product. So you should sort of think of it like, another way of think of it as well is if you just look at the terms where beta is 0, that's the usual cup product. So you should think of this as some sort of like enlarged deformation or something of the usual cup product. Here's these additional terms. Okay, oh yeah, so I just said this. Okay. So that's quantum, the small quantum cohomology group. And then there's also a big quantum cohomology group, which I'm not going to explain, but basically you count curves passing through an arbitrary number of cycles. So this sort of Novikov ring is way bigger and it's a lot more data. Okay, so here's a conjecture by Morrison and Rouen. Any two birational Calabi-Yau manifolds have the same quantum cohomology groups. And then there's this additional word up to an analytic continuation. So Morrison sort of at least stated this in dimension 3, and Rouen conjectured this in all dimensions, I think. Why do I say analytic continuation? Well, there's a technical point, which is if I have two birational Calabi-Yau manifolds, when I define quantum cohomology, I have to choose a symplectic form, a Kähler form. It depends on the choice of the Novikov ring is defined using this Kähler form. I'm completing using the Kähler form. So it sort of depends on this choice of Kähler form. And the problem is that the Kähler form on one Calabi-Yau manifold might be completely different to the one on the other one. And so you need to compare the two quantum cohomology groups somehow. And the usual way is to sort of analytically continue somehow from one to the other. So, you know, you have these two Novikov rings, and maybe the power series in some direction formally converges, and then they're the same once you sort of evaluate in that sort of direction. Okay, so Li and Ruan proved this in dimension 3. And Yuao Li, Lin, Ku, and Wang proved this for particular birational transforms called ordinary flops, which I won't explain. There's a very basic birational transform for Calabi-Yau 3 manifolds called an Atiyah flop. And you can sort of think of this as you have some Calabi-Yau 3 manifold and a sort of embedded P1, and it's kind of like a zero surgery. You sort of cut out the P1 and glue it in a different way. Okay. So I have my birational Calabi-Yau manifolds, and I have these two Kähler forms, omega and omega hat on X and X hat. And then, well, then I have the associated Novikov rings. So group completions of H2 of X and H2 of X hat. And remember, I said H2 of X is equal to H2 of X hat. And so, well, if I want to compare the Novikov rings, one thing I can do is just take their intersection. Once I've identified these H2 groups. And here's the main theorem. There exists a graded algebra over the intersection of these Novikov rings. I call it Z, so that when I tensor with one of the Novikov rings, I get quantum cohomology of X. And when I tensor with the other Novikov ring, I get the quantum cohomology of X hat. Okay. Let me explain in the last few minutes, let me explain the proof, the idea of the proof. Okay, so obviously, as I was sort of hinting quite heavily, the key idea is to use Floer Cohomology. Hamiltonian Floer Cohomology for a closed symplectic manifold is always just the cohomology. In this McKay correspondence example, it wasn't. I took some sort of increasing Hamiltonian because it was a non-compact. Why was this non-compact variety? But here, these Calabi-Yaus, they're projective. And so Hamiltonian Floer cohomology is just cohomology. And there's a product on it called the Pants product. And remember what I said, when I compute the differential in Hamiltonian Floer cohomology is you're counting these cylinders connecting orbits, and they satisfy some PDE. And to do a product, you have a pair of Pants, and you count those satisfying a similar PDE, and you get a product. And then for any Hamiltonian H on X, Floer cohomology of H is quantum cohomology, and similarly for X hat. And in general, it's true for any closed symplectic manifold. Okay. So what I want to do is I want to choose appropriate Hamiltonians on X and on X hat, so that somehow it becomes maybe a bit clearer why these quantum cohomology groups are the same. Okay. So that's what I want to show. I say there's an isomorphism between them, but really, I mean, these Hamiltonian Floer groups are defined over these Novikov rings, at the same Novikov rings as before. And so when I say HF star H and HF star H at are the isomorphic, I really mean they're isomorphic in the sense that I sort of explained earlier with the quantum cohomology groups. So I want to find another group Z, which is like a Floer group defined over the intersection of the Novikov rings. So I tensor with one, I get HF star H, and when I tensor with the other, I get HF star H hat. But I'll just say it. I'll just say this to smooth things out. And remember, two birational Calabi-Yau manifolds, X and X hat, are isomorphic outside codimension 2 subvarieties, and I want to use that fact. So the first thing I want to choose away from V and V hat, which is the region where the birational transforms are ill-defined. I want to choose some sort of affine subvariety. Okay, X and X hat are projective. I can do this. And I've called A in X and A in X hat, so I've just called it A in both sides. Okay. So, well, I want to compute this Hamiltonian Floer cohomology group on both sides. And what I want to do is choose an appropriate Hamiltonian. So what I'm going to do is I'm going to put one Hamiltonian H on X and one Hamiltonian H on X hat. And schematically, they're going to look like this. So inside a large compact subset of A, they're sort of less than 0 and very small. And then they grow rapidly to a large constant, sort of near the divisor at infinity, sort of region X minus A and X minus A hat. And I want the Hamiltonians to be constant in that region. Okay, so that's what the Hamiltonians look like. Okay. Now, actually, let me go to the last slide again. So we have these large constant orbits, and for the moment, I'm going to pretend that I can ignore them. You can't ignore them, but I'm going to pretend that they're not part of the Floer chain complex. So I'm going to ignore the constant orbits away from A. Okay. So basically, the generators of the two Floer complexes are identical. Again, there's some work there needed to be done because the two symplectic forms, omega and omega hat, are different. But you can sort of make them the same on some sort of large compact subset of an affine subvariety if it's common. And so the dynamics can be made the same as long as you ignore these constant orbits. Okay. Okay. Now, since V and V hat are of complex codimension 2, which is real codimension 4, the Floer trajectories, so these cylinders and these pairs of pants, generically, they don't intersect, they don't hit V and V hat where the birational transform is ill-defined. Because this is codimension 4, but these are two-dimensional objects mapping to X and X hat. So generically, they don't hit. So you can sort of make them sort of avoid V and V hat. And hence, these Floer algebras are the same. That's sort of the moral argument. Okay. Now, there are many technical issues. Oh yeah, so here's the schematic picture. So A is the common affine variety. A is this red circle. Inside A, I have identical orbits. So that means the chain complexes are the same. And then I have Floer trajectories that connect these orbits, and these sorts of Floer cylinders. So these cylinders, these gradient flow lines for Hamiltonian Floer cohomology connecting these orbits, they may go outside A and come back into A and connect these orbits, but generically they avoid the sort of region V and V hat where the birational transform is ill-defined. Okay. So in the last few minutes, I'll explain what are some of the additional technical issues. So one issue is I can't ignore these orbits that are really high. You just can't ignore them. They do contribute. Also, if you just have a region of your Hamiltonian, which is just constant, like an open region where it's constant, say, well, then the associated action functional isn't even Morse. So sort of you can't do the sort of equivalent of Morse homology. So, you know, in general, you need to perturb it generically, and so it's Morse and so on. But we can sort of get around this. But one thing we need to do is, instead of just using a fixed Hamiltonian, we need to take a direct limit as these Hamiltonians get bigger and bigger and bigger, and sort of take the direct limit of those chain complexes, and somehow these, you know, if you have some constant orbits that do contribute, then somewhere up in this direct limit, they sort of stop contributing. So that's the first thing. And also, at this point, to ignore these constant orbits, you really need C1 is 0. You sort of really need that condition. You can't just do this for any affine subvariety inside any projective variety. In that case, orbits, there's no way of getting rid of these constant orbits, but for the Calabi-Yau case, you can. Yeah. Okay. Yeah, that's what I said. Okay, so in the remaining few minutes, I could just explain some further directions. So there's a connection between, so the McKay correspondence, I had a resolution of an orbifold singularity, and you could think of this resolution as a birational morphism between orbifolds. Well, a birational morphism between a Calabi-Yau manifold and a Calabi-Yau orbifold. And so one might wonder, can you compare the quantum cohomology groups of birational orbifolds? And well, if you try to do that using this proof, there's an issue, which is they're no longer birational outside codimension 2 subsets. So remember on the previous slide, I had V and V hat where the birational transform was ill-defined, and you know, with this crescent resolution, my like V or whatever is a divisor, it's codimension 1, and so these Floer trajectories connecting these orbits actually do intersect, say, V, and that causes problems. So there's not going to be a statement showing that the quantum cohomology groups of these orbifolds are the same, but there might be a way of correcting that somehow. Okay, thank you for your attention.
Thanks a lot. I think we have, oh, so it cuts again. Well, I guess since we no longer have a feed, we finish this session, and well, I thank you all for participation and for your